Hey, and welcome back. Today we're gonna count till infinity. Well, not exactly counting, but we'll add till infinity. And that's not an easy task. To do that, we'll have to pull some tricks. But first of all, let's define a series. A series is the infinite summation of terms. If we just have an infinite amount of terms, we can add them up and basically sum infinite amount of terms. So all we need is infinite amount of terms. So let's bring back the sequence, the same sequence we saw in previous lessons. an when n goes from 1 to infinity. a1, a2, a3, and so on. Now, all we need to do is sum all these elements together. We can start with a1, add to that a2, add to that a3, and so on till infinity. Okay, now we have a series, an infinite sum of elements. In short, we'll just write sigma and goes from 1 till infinity of an. However, there's a problem here. We're trying to add infinite amount of terms. Not only that it's difficult, it's actually not allowed. The plus sign works only for a finite amount of terms. So we need to find a way to get around it and find a different way to basically add till infinity. So we'll do a little trick. We'll sum only m elements and not infinite amount of elements. We'll sum only the first m elements of the original sequence, a1 plus a2 plus all the way till am. The summation will depend only on the value of m. Let's see how it works. If m equals 1, we're summing the terms from a1 till a1, so basically it's a1. If m equals 2, then we sum from n equals 1 till 2. We get a1 plus a2. If we continue this way and we let m be 3, this time we count from n equals 1 till 3. Basically, we get a1 plus a2 plus a3. I think we get the idea. Now, we're not at infinity yet, but we're getting there. Now, this is where things get a little bit tricky. What we did create here is a new sequence, the sequence Sm. This sequence is called the sequence of partial sums. Now, what we did here was using an original sequence an to create a new sequence, the sequence of partial sums. Now, we should view it as a sequence. That means also asking ourselves if it has a limit. And in our case, if it has a limit, when m goes to infinity, basically what we got here is the original series we were looking for. So I know it might be a little bit confusing, so let's understand it through an example. So let's bring back a sequence we know really well. an is 1 over n, which is the elements 1, half, third, quarter, and so on. This sequence will lead us and show us how this works. Now we need to remember we have two sequences. The first one, an. That's the original one. And we have Sm, which is the partial sums. And it is its own sequence, with the general term being sigma and runs from 1 till m, 1 over n. That means that the first term would be 1, second one would be 1.5, the third one would be 1 plus half plus third, just like we saw before, and so on and so on. As usual, if we see what we're doing, we'll understand it. So let's create another graph for our second sequence, our sequence Sm, and understand exactly how that looks like. So our left graph is going to be the graph of the sequence an, whereas the right graph is going to be the graph of the new weird sequence Sm. Now, an is 1 over n. We already know how that sequence looks like, and we know that the first term is 1. Which is also the first term of Sm. What happens when we go to the second term? Well, a2 is half, but s2 is 1 plus half. Basically what we're doing, we're summing the two terms of an. Let's continue on. What about s3? Well, we know a3 is 1/3. s3 would be 1 plus half plus 1/3. That's the idea. If we continue on to S4, well, obviously we'll get 1 plus half plus third plus a quarter. And we can continue like that till infinity, basically. But there are a couple of points that are really important right now. The first one is to understand that the general term in Sm is being received by just summing the first m terms of an. Now in this case, an is a positive sequence. All of its terms are greater than 0. What this creates is a new sequence, Sm, that is strictly increasing, because every time we move forward with our general term to the next one in Sm, we're basically adding another value from an. In this case, it is positive, which in return gives us an increasing sequence. So now we see that Sm as a sequence has properties as any other sequence. And in this case, one of the properties that it has is that it is an increasing sequence. And now another question arises. Does Sm as a sequence converge to a limit? If so, that would be the value of the original series we started from, that infinite amount of summation. And that's what we wanted to do all along. Now, we're not going to calculate the limit of a series in this lesson, but we now get the idea behind a series with positive terms. Now, intuitively, we can kind of see that what's going to determine whether the series converge or not is the mth term of an, basically the last term that is being added to Sm. If this am is very small, then there's probably a chance that our series does converge. Whereas if it's quite large, then intuitively we can assume that the series will not converge. Now that we understand this, let's take it another step. Let's look at a series that is being created out of terms that are not necessarily positive, real numbers, but we're gonna focus on a specific important example, a series where the terms change their sign from plus to minus and so on. Now, since we know that a series always starts from a sequence, so let's first define our sequence from which we're gonna build the series. We're gonna take the sequence minus 1 to the power of n plus 1 over n. That would be the sequence 1 minus half plus third minus quarter and so on. Now our series that is built upon this sequence, it changes a little bit. The general term is sigma n goes from 1 till m of minus 1 to the power n plus 1 over n. And now the first, second, and third terms are 1 minus half plus third, and so on. Now let's see what we get. The graph on the left, just like before, is going to represent an. So the terms are going to be 1 minus half, a third minus quarter, and so on. On the right, we get Sm. So let's see what we get. The first term, well, that's just 1. But the second term now gets 1 minus half. Although S2 is A1 plus A2, Sm is no longer an increasing sequence. S3 would be 1 minus half plus a third, and so on and so on. Looking at this sequence, we can see it behaves a little bit different than the sequence we had before, where an were all greater than 0. And intuitively, we can say that the chances for this sequence to converge are probably higher than the previous one. Now, the interesting thing is that if this series does converge, the limit would be somewhere between the value of S1 to S2. Not only that, it would be somewhere also between the value of S2 and S3. Also between S3 and S4, and so on and so on. We can narrow down on where the limit's supposed to be. And it all depends on an, our original sequence. The sequence we built the series from. And that's how, indirectly, we can sum all the way up to infinity. One last important point is to notice that both sequences we saw today, this one and the previous 1 over n, both of them have a limit. It's 0. If they didn't have a limit, or the limit wasn't 0, we would know that the series does not converge. This is an important condition for a series to converge. the sequence, that original sequence, has to converge to 0. It also feels intuitively true because we're just adding more and more terms. If they don't go to 0, our infinite summation will probably not converge. Now, what dictates whether our series converge or not is how fast an goes to 0. But that's a topic for another video. So I hope you enjoyed it. Leave a comment if you have any, and I'll see you next time.